Welcome to This Explainer. Today, we're diving into the incredibly high-stakes, precision-engineered world of special agent fire extinguishing systems. You know, if you've ever looked up at the ceiling of a massive data center, a museum archive, or an industrial chemical plant, you might have noticed you don't see your standard sprinkler heads up there. And there's a very good reason for that. In these highly specific environments, standard fire protection just isn't going to cut it.
So think about this for a second. What actually happens when you throw water on a roaring grease fire in a commercial kitchen? Or what would happen if hundreds of gallons of municipal water suddenly dumped all over a multi-million-dollar rack of energized IT servers? Well, in these specific environments, water isn't just an ineffective tool, it's literally a disaster waiting to happen. It can violently spread the flames, conduct lethal amounts of electricity, or just permanently destroy the exact thing it was supposed to protect.
And this right here brilliantly illustrates the fundamental difference we're dealing with. A traditional water-based system is generally just designed for fire control or containment, basically keeping things manageable until the fire department rolls up. But special agent systems, they have a much heavier burden. Their objective is complete and total extinguishment, and they have to pull it off with a highly limited, meticulously calculated quantity of extinguishing agent. There is no endless supply of water from a fire hydrant here. They get exactly one shot to get it right. Okay, let's take a quick look at our roadmap for today. First, we'll cover when water fails. 2, the anatomy of dry chemical systems. 3, wet chemicals and kitchens. 4, invisible protectors, clean agents. 5, the lethal power of CO2. And finally, 6, foam systems for massive fires. Let's jump into section 1, when water fails. These locations we're talking about represent billions of dollars in infrastructure, not to mention priceless cultural heritage. We're talking about commercial kitchens dealing with superheated oils, chemical storage facilities packed with water-reactive metals, data centers that basically house the backbone of the internet, electricity-generating plants, and museums holding totally irreplaceable artifacts. In all of these spaces, dumping water is either chemically reactive, electrically conductive, or just destructively ruinous. That is exactly why these environments strictly require engineered special agents. Moving right along to section 2, anatomy of dry chemical systems. Now, what's really fascinating here is how incredibly precision engineered these setups are. The storage containers, which hold the agent and a pressurized expellant gas like nitrogen or CO2, they have to be maintained in very specific temperature ranges, typically from -40 to 120 degrees Fahrenheit. And the piping itself, it's mathematically engineered to account for the unique flow characteristics of the chemical agent. That means the exact number of bends, the fittings, and the pressure drop or friction loss are all meticulously calculated into the design beforehand. Even the nozzles must be specifically listed by NFPA 17 standards for their exact intended use. So there are absolutely no standard one-size-fits-all nozzle designs here. So how does this precise machinery actually spring into action? Well, first, a fire detection device senses the hazard and triggers an alarm. This is often an audible warning signal to facilitate prompt evacuation of the area. This immediately activates a mechanical or electrical release mechanism. Then, that highly pressurized expellant gas violently forces the dry chemical agent through that friction-calculated piping and right out the nozzles. Crucially, the vast majority of these fixed systems, which, by the way, can also be triggered manually, are tied directly into the building's infrastructure, so they automatically shut off the fuel and power to the hazard area the very moment they actuate, completely isolating the threat. All right, on to section 3, wet chemicals and kitchens. If you're a fan of practical chemistry, you are going to love this part. Commercial kitchens are constantly dealing with deep fat fryers and heated oils, which create incredibly stubborn Class K fires. To fight this, wet chemical systems use a brilliant process known as saponification. Basically, when the liquid agent, which is usually a potassium-based mixture, hits the burning fats and oils, it causes a rapid chemical reaction that converts the hazard into a non-combustible soapy foam. It extinguishes the fire by smothering it, cooling the hot oils, and inhibiting the flames all at the exact same time. It literally turns the fire hazard into harmless soap. Section 4, invisible protectors, clean agents. Clean agents are specifically deployed in places like computer rooms, telecommunications hubs, clean manufacturing rooms, document archives, and fine art storage labs. These agents, which include halocarbons and inert gases, are electrically non-conductive and, best of all, they evaporate completely without leaving a single trace of residue behind.
They are truly the silent, invisible guardians of our modern digital infrastructure and our historical heritage. They allow a fire to be completely extinguished without destroying the sensitive equipment or priceless documents in the room. Next up, Section 5, the lethal power of CO2. So, taking a much more serious tone here, CO2 works primarily by displacing the oxygen in the environment, effectively suffocating the fire. But naturally, by eliminating oxygen for the fire, it completely eliminates breathable oxygen for humans. To actually be effective in a total flooding application, CO2 has to reach a concentration of at least 34% in the room. And it's important to understand that concentration is instantly lethal to human beings. These systems carry immense, absolute life-or-death stakes. Because of that lethal power, strict, mandatory safety protocols are an absolute necessity. You cannot just rely on alarms alone. You need pre-discharge alarms to give people time to evacuate safely, and that has to be paired with comprehensive, rigorous personnel training. Furthermore, NFPA standards require annual room integrity tests. Think about it. If a room has leaks or if the HVAC dampers don't automatically close like they're supposed to, that lethal, invisible gas could easily escape into adjacent, occupied spaces, creating a completely undetectable, suffocating atmosphere. Which brings us to Section 6, foam systems for massive fires. When you're dealing with massive flammable liquid hazards, foam systems are deployed, and they basically come in 4 different setups. You have your fixed systems, which are fully automatic and piped from a central station directly to the hazard. Then semi-fixed systems have the piping in place, but they require a fire truck to actually hook up and pump the foam in. Next, you have mobile units, which are typically wheel-mounted, and finally, portable setups, where trained personnel physically transport the hoses and nozzles directly to the fire. Now, creating high-quality firefighting foam isn't just mixing some soap and water in a bucket. It requires intense mechanical agitation and precise mixing of water, foam concentrate, and air. And to do this, you need highly specialized proportioners. Whether it's a balanced pressure proportioner that perfectly matches the water pressure or an around-the-pump system on a mobile rig, these complex mechanical devices are specifically engineered to eject the exact percentage of concentrate into the water stream, usually somewhere between 1 and 6%, to create the absolute perfect smothering blanket of foam. And this right here perfectly illustrates our entire journey today, matching specific, complex hazards to their highly engineered solutions. A commercial kitchen gets the saponification of a wet chemical. A massive liquid fuel spill in an aircraft hangar gets a smothering blanket of foam. The delicate, expensive electronics of a server room gets a residue-free clean agent. And the rapid spread threat of a flammable liquid room gets a fast-acting dry chemical. It's like a giant puzzle where every piece has a very specific place. We have seen just how specialized, engineered, and critical these systems are. They rely entirely on limited quantities of agents, precise friction loss calculations, and absolutely perfect automated actuation, which leaves us with this final thought. If these limited quantity, one-shot systems are our absolute only defense in these high-stakes environments, what happens if they're rigorous maintenance, inspecting for mechanical damage, checking the precise aim of a nozzle, or verifying cylinder pressures? What happens if that's overlooked for even a single day? The stakes, honestly, couldn't be higher. Thank you so much for joining me on this explainer, and keep learning.